Good afternoon. My name is Charles Gillott, and I'm a civil and structural engineer, but also a researcher working with the University of Sheffield, attempting to both understand and accelerate a transition to a circular economy within the built environment. Today I'm probably going to take a bit of a bigger picture view and introduce this concept of circular economy potential and look at how we can apply this to existing buildings across different geographical and spatial scales. Before we do that, I'd like to establish a shared understanding of exactly what we mean by a circular economy. Typically, most definitions of a circular economy have some reference to the narrowing of resource inflows and waste outflows, and typically achieving this by maintaining material at a high value for a long period of time. This notion can be traced back to 1982 with the self-replenishing system proposed by Walter Starhall. This suggests 4 concentric replenishing loops in order to maintain material at a high value. Somewhat familiarly, these are named reuse, repair, recondition, and recycle, where each concentric loop should be prioritized ahead of the next one in order to make material maintained without using more energy. If we fast forward 4 decades, well, around 4 decades from that point, we can see that despite many comparative, contrasting, and complementary definitions of a circular economy, we find ourselves largely with the same understanding of what this is. Yes, the Ellen MacArthur Foundation diagram is a bit more colourful, and we have a separate loop for renewable materials, but many factors stay the same. We have our concentric loops and the need to prioritise these in terms of the tightest loop, maintaining the maximum amount of material for as long as possible. Similarly, these are very similarly named, where we have reuse, repair, remanufacture, and recycle, going up from not 3 to 4 to 5, but to the 13 R's that we heard about earlier. So considering this in-depth and fairly consistent understanding of the circular economy and what that means, you'd expect that understanding the circular economic potential of a building is something that's relatively easy. Surely this is just its ability to be repaired, reused, and recycled. Unfortunately, as I'm sure you're all aware, this is not the case. And this is largely because our buildings aren't simple products such as water bottles, carrier bags, or coffee cups. They are, in fact, complex systems and systems of systems with interdependencies and interconnections. This makes things a lot harder. Not only are buildings buildings, but they're actually themselves made up of layers and assemblies. Some of these might be abstract, such as skin, surfaces, and space, or some might be more tangible, such as the roof, a wall, or a floor. These layers and assemblies are themselves made up of components or groups of components. And components themselves often made up of one or more and multiple materials. What this means is that the circular economic potential of a building is not governed just by the reusability, the repairability, and the recyclability of one component, but that of many. And also the layers and assemblies that those components comprise and the materials making up those components. What this means is that rather than one, we actually have 2 hierarchies at play when attempting to understand circular economy within the built environment. Not only do we need to look at retaining value within the built environment, as was suggested by Starhall all those years ago, and also the Ellen MacArthur Foundation more recently, i.e. the value that's retained within the system, but we also need to look at the amount of material that's flowing through that recirculatory loop, i.e. the quantity of material being retained at that value. This leads us to a combined hierarchy where we have to consider both end-of-life scenarios, but also spatial and geographical scales at the same time. Similar to as we've seen earlier today, we can simplify the hierarchy for the built environment circular economy to something similar to this. First up, in order to ensure that a maximum amount of material is retained within the built environment, but also that this material is retained at high value, we should look to reuse entire buildings, and where that isn't possible, individual layers within that building. Next, we could look to deconstruct the building, using assemblies of components within that, or individual components as they are, taking a beam or a brick out of a building and using it as a beam or a brick. Only when we've exhausted this opportunity should we look at breaking materials down into their constituent elements and look ideally at recycling these, melting a beam back down and turning it into a different beam that we have a use for, but eventually downcycling these, melting a structural element down and turning this into something perhaps not of structural grade. Then and only then should we be looking to consider landfilling, incineration, or energy recovery. What this hierarchy means is that the circular economic potential of a building is actually how far up towards the top of this the building, its constituent components, and constituent materials sit. What this means is that if a building is made up of materials that themselves have a very low reusability, and they're in components that also cannot be reused, this doesn't preclude the building from having a huge circular economic potential that then filters down to the materials sitting within them. To give a bit of an example of this, I would like to introduce Park Hill housing estate, which is in my hometown of Sheffield. This was constructed in the late 1950s, early 1960s as a social housing estate. It's huge, huge development. It contained in its heyday 995 flats, 31 different shops, and also 4 pubs. Unfortunately, for various different reasons, as it moved to the 1980s, things started to get more dilapidated, more derelict, and it sat empty and largely vacant throughout much of the preceding decades. Fortunately, and somewhat controversially, in 1998, Park Hill received listed status as a Grade 2 listed building, and this actually at the time made it the largest listed building in the whole of Europe. So a huge, huge amount of material, and also a huge, huge amount of embodied carbon. Since that listing in 2010, and again in 2020, elements of the building were refurbished, reopened, and put back into use. And it's now actually sitting at about 90% occupancy. What this story tells us is that even though the brutalist concrete frame of Park Hill had very little recyclability potential, and we were unable to go in there and take out components for reuse because of its in situ nature, all that material was able to be retained and had a circular economic potential much greater than the sum of its parts because of the building it was in and how that material was being reused. Examples such as Park Hill are relatively common, and what they do is highlight a bit of a gap in how we're currently assessing circular economy and circular economy potential, both within practice but also in research. As we've heard today, we're getting better and better at understanding the reusability of components and the recyclability of materials and assemblies of those through things such as EPDs, bills of materials, and more recently, material and building passports. But what these don't do, perhaps as often, is consider the buildings in which these materials are in and how they could be reused. Similarly, on the research side that I'm perhaps more familiar with, we are able to use industrial ecology techniques such as urban metabolism, material stock analysis, to start to understand the amounts of reusable and recyclable materials in cities and regions, entire nations, or across the globe as a whole. But again, what we don't consider is the actual buildings that those materials are in and how the circular economic potential of those could far supersede the sum of the potential of the materials within those buildings. If we think back to the hierarchy that I put on the screen and we've seen a few times earlier, this is particularly concerning because we know that retaining, refurbishing, and reusing buildings actually serves, typically, to maintain a maximum amount of material, but also maintain that material at its highest value, providing the greatest service to society. In other terms, what we're currently doing, although it's very, very valuable, is only really asking the first in a long series of questions required to understand the circular economic potential of our assets and our built environment as a whole. More simply, we're quite good at asking how much of which materials are where. This is very useful. It helps us to answer questions both in research and in practice. For example, in research projects, we're able to estimate tonnage or volumes of different material categories spread across the UK or the globe as a whole. In practice, we can understand which types of elements or which weights of different materials we have in areas of a building, the roof, the wall, the floor. But there are still gaps in this. What we're not currently asking is how these materials are and could in the future be used. What is their current role and what is their potential future role within the built environment? For example, understanding not that we have a certain tonnage or weight of concrete, but that actually this concrete is currently being used in a structural frame within a building that's over-designed, able to be adapted and reused for residential purposes in a prime location in Sheffield. This is something that would have been previously overlooked had we not prioritised adaptive reuse over simply material reuse. It's only when we start to ask these questions and understand the circular economic potential of individual materials is not governed just by themselves, but how they are used within society, that we can understand their true CE potential. Ultimately, this is what's required in order to measure and advance our progress towards a circular economy within the construction sector as a whole. Thank you very much.